Okay, so last time we had talked about units. Let me very quickly remind you of some things. So here's sort of a summary. We talked about how there are three fundamental quantities in mechanics. And let me also do this. Is this better? Yeah. There are three fundamental quantities in mechanics: length, mass, and time. And then everything else can be built out of that. So if you talk about, for example, speed, that is the amount of distance covered in some amount of time. So it involves a measurement of length and time. What's the attendance code? It was, what was it?
7312.
7312. 7312. Maybe someone can type that in the chat in case. So we had this SI system of units, which is the one that we will use most often in this course, where length is in meters, mass is in kilograms, time is in seconds. Then there's CGS, where you have centimeters, grams, and second. And then the US customary, where you have length in feet, slugs, and seconds. And then here are some conversions. Once you define what is a meter, a kilogram, and a second, using either fancy ways or just assigning, for example, the mass of a block sitting in Paris somewhere as being 1 kilogram. Once you fix these definitions, then these other units are simply defined in terms of these SI units. So when I say what is a centimeter, I just mean it's the thing where 100 of them is equal to 1 meter. What is a gram? It's the thing, it's a unit where 1,000 units of grams is equal to 1 kilogram, and so on. Any questions on that? So we did some unit conversion problems last time, so let me just do a quick recap here. So for example, if we want to do 55 miles per hour, we want to convert that to kilometers per hour. You can look up in Google that 1 kilometer is defined, a mile is defined such that there are 0.621 miles in 1 kilometer. And so if I want to convert this into kilometers per hour, what I do is I take my 55 miles per hour and I just multiply it by 1. Just give me a second here. I multiply it by 1, and I just take this 1 and I write it as the ratio of this 1 kilometer divided by 0.621 miles. Because they're equal, their ratio is 1. And then you see that the miles here and the miles here cancel. You're just left with kilometers per hour. Multiply these two numbers, you get 89 kilometers per hour. You had a choice here. You could have taken this 1 and written it as this inverse ratio, but then you wouldn't have arrived at kilometers per hour. You would have arrived at some other units, which are weird. Okay, so that's how you kind of know how to do this. Okay. Then we did one example with 35 meters squared last time. Here you have meters squared instead of just meters, which you can think of as meters times meters. And you want to convert each one of these meters into centimeters. So I will take multiplied by 1 times 1. This ratio here will convert one factor of the meters into centimeters, and this ratio here will convert the other factor of meters into centimeters. So you get here, there's 100 centimeters per meter, 100 centimeters per meters. Meter squared cancels with meter, meter, and then you're left with centimeter squared. And then you get 35 times 100 squared, which is 10,000. And so that's 35 meters squared is equal to 350,000 centimeters squared. So if you want to impress people about the size of your house, you can give them your answer in centimeters squared. It's 350,000 centimeters squared. Okay. Let's do another example. This is sort of a top hat question, just so you guys can get some practice with this. The diameter of the hydrogen atom is known to be about an angstrom, which is 10 to the minus 10 meters. So the question here is, what is the diameter of the hydrogen atom in miles? So see if you can figure this out. Feel free to help each other out. Let me go to top hat here. Oh, wait, do I not make this up? I can't remember if this is a top hat question or not. Actually, it's not. So maybe take a moment. So here's some hints on the screen. You want to go from meters to miles. And the hints on the screen I'm giving you is that you can go from meters to kilometers. And then from kilometers, you can go to miles. Those are the two conversion things you can look up right there. So see if you can figure out what is the, yeah, so it's not a top hat question. So if you get an answer, feel free to blurt it out or type in the chat. Anybody have an answer? Yep.
6.21 times 10 to the negative 14.
6.21 times 10 to the minus 14. Someone else in the chat also has that answer. Okay, we got 3 people, 4 people. I actually don't remember the answer, so let's see what it is. Yes, it is in fact 6.21 times 10 to the minus 14. So basically, what I'm doing here is, this is one way of doing it, where I know to go from meters to kilometers, and then I know how to go from kilometers to meters. Let me actually switch screens here. And so what I'm doing here is I'm multiplying by 2 factors of 1. And this first factor of 1 is 1 kilometer divided by 1,000 meters. So in this multiplication here, I'm going from meters to kilometers because these meters cancel and I'm left with kilometers. Then I'm left with kilometers. So now I multiply by another factor of 1, which is this ratio, which then takes me from kilometers, they cancel, to miles. That makes sense. So then in the end, you see that the meters cancel, the kilometers cancel, all you're left with is miles. So I'll put that together, all these numbers, you get 6.21 times 10 to the minus 14 miles. Which means that if you were to take 1 mile, you could line up hydrogen atoms along that entire mile. What would you have? You would have 1 over that many hydrogen atoms. So 10 to the 14 atoms divided by 6.21. So forget the 6.21. What's 10 to the 14 atoms? That's 100 trillion hydrogen atoms roughly in a mile. Any questions on that? Okay. All right, so this next one is a top hat question. So this is sort of an interesting question. The distance to Proxima Centauri, which is it's the name of a star that is closest to us after the sun. So the next nearest star after the sun. It is a distance of about 4 times 10 to the 16 meters from Earth. We want to convert that into miles. How many miles away from Earth is Proxima Centauri? Again, we have the conversion from meters to kilometers and kilometers to miles. So this is an image of the star from the Hubble Space Telescope. Let me switch to top hat here. Okay, so this is a question. Maybe I'll give it 2 minutes. One minute. Yeah. Say it again. Your phone won't connect to your laptop? Oh, okay. Send me an email after class and try to fix it. Or maybe after time's up, you can announce your answer to the whole class and see. Okay, let's see what we got. Do you want to announce your answer? Take that as a no. I was going to ask you if you wanted to announce your answer. Did you get B? Okay, all right. B is in fact the correct answer. So some of you got C. Well, I wonder where that is coming from. It's a factor of 10 to the 6. Okay. So let's unpack what happened there. The correct answer is B. That is 25 trillion miles, right? 2.5 times 10 to the 13 is 25 times 10 to the 12. 10 to the 12 is a trillion. So the nearest star to us after the sun is 25 trillion miles away. Any questions on this? right? What you would do is you would take your 4.0 times 10 to the 16 meters. You would then convert the meters into kilometers. So you would have 1,000 meters in 1 kilometer. And then you would convert your kilometers to miles. And so you would have here 1 kilometer is 0.621 miles. And then your meters and meters cancel, kilometers and kilometers cancel. And so you're left with 4 times 0.621 divided by 1,000 miles. And if you do that, that's you get the questions on that. Okay. Now, actually, maybe hopefully you didn't see the slide that I just. Anyone of you see it? Okay. If you saw it, be quiet. Just a random question. If we were to try to go to this next nearest star in a current spaceship of ours, how long do you think it would take us to get there? With our current technology, it's not a physics question, it's more like just how capable do you think we are, and how big do you think 25 trillion miles is, kind of a question. So, say it again. A long time is correct.
I think you said that the moon is 3 trillion miles away, and it takes astronauts about 3 days to get there. So 1 day would be 1 trillion miles. So I guess when you 25 days.
Wait, the moon is 3 trillion miles away? I'm not sure. I don't think that's. I mean, the sun is 93 million miles away.
Oh.
So the moon is a lot closer.
Right. I know that I think I remember reading one time as a kid that it took the astronauts 3 days to reach the moon.
Yeah, I actually don't know how long it takes to get to the moon. Several months to get to Mars. So maybe I'll do this. I'll go in powers of 10. How many people think it'll take 10 years to reach the star? 100 years. Okay, kind of, maybe 1,000 years. A few hands. 10,000 years. 100,000 years. 1,000,000 years. Okay, 1 for 1,000,000 years. 1,000,000,000 years. No idea. How many people have no idea? So, the correct answer is about 100. Say it again.
78,000.
Okay, that's actually pretty close. Yeah, it depends on the exact speed of the spaceship. But it would take us about 100,000 years. About 100,000 years. If our current spaceship goes at about 30,000 miles per hour, which is typical, the thing that we sent to Pluto a few years back, that's roughly the speed that it goes with. So if we were to go with that, it would take us 100,000 years to get to the next nearest star to us after the sun. Think about how insane that is. You're going to be traveling. You will die 1,000 times before you hit the next nearest thing in space, like the next nearest star. Okay. And it gets worse. Anyone know what this image is? It's pretty famous. It's the Hubble Ultra Deep Field. It's sort of a boring picture if you don't have context for it. It's just space with a bunch of glitter in it. But what this image is, you can think of it as follows. That if you were to go out at night and you were to find an empty patch of sky where you don't see any stars or anything like that, it's pitch black. And if you take a little cardboard box and you make a little tiny hole in that piece of cardboard, and if you hold it out at arm's length pointed at that patch of empty sky. And if you look through that tiny hole, if you had eyes as powerful as the Hubble Space Telescope, you would see this image. Meaning that that tiny little black dot that you would see with just your eyes is actually filled and littered with all of this points of light. Each one of these points of light is a galaxy. I think the ones that flash a little bit more, maybe nearby stars. But for the most part, like that's a galaxy, that's a galaxy, that's a galaxy. Each one of these points is a galaxy. Then you can imagine taking your piece of cardboard with a tiny hole in it and just moving it over a little bit, and you get another image like this. And then you can imagine mapping out every single point in sky. And in fact, when the people that took this image, the team of scientists, they wrote a proposal to NASA because they all fight for telescope time, right? So there's this Hubble Space Telescope and everyone wants to use it. They want to point it at different things so they can do their own studies. This group made the proposal that we want to point it towards where there is nothing, right? Just imagine how crazy that proposal is. Everyone's like, I want to point it to that little planet over there and this galaxy over here because I want to learn this and this and this about it. And they're like, we want to point it towards where there is absolutely nothing. But fortunately, they made a convincing case that we want to actually see if it's really nothing. And in fact, it's a pretty insane picture. And there are trillions of galaxies in our observable universe. So if you can now imagine that if there's some alien civilization in another galaxy, maybe there's someone in this galaxy here, maybe they have their own Hubble Space Telescope. And if they pointed in our direction, they would also see something like this. And we would be one of these points of dots. We would be maybe that galaxy right there. Maybe that's us from their point of view. Now, when I said that it takes us 100,000 years to get to the next nearest star, what does that mean? Well, we are part of the Milky Way galaxy. Maybe I should go to the next slide here. Let's get some distances in our head. The distance to the sun is about 93 million miles. The distance to the next nearest star is about 25 trillion miles. It's about 4.2 light years, meaning that if you turn on a flashlight pointed at Proxima Centauri, it'll take that beam of light to reach 4.2 years to reach Proxima Centauri. And with our current spaceships, it would take us on the order of 100,000 years to reach Proxima Centauri. So these numbers might make us feel a bit insignificant. Or you can look at it in a more positive way that takes the pressure off. None of this matters. So just relax, enjoy. But it gets worse because our own Milky Way galaxy is about 100,000 light years across. So our sun is a collection of stars in the galaxy called the Milky Way galaxy. And our sun is somewhere over here, like one little dot. There's about 200 billion stars in our own Milky Way galaxy. So our sun is one of about 200 billion stars in our galaxy. And the size of our galaxy is about 100,000 light years across. What that means is, if you are, say, at this end of the galaxy here, you turn on a flashlight, the beam of light will travel across the galaxy. For it to reach the other end, it would take 100,000 years. Imagine coming into this room, turning on the lights, having to wait 100,000 years, you die 1,000 times, and then the lights come on. That is how big our own galaxy is. And if you do the math with our current spaceship, 30,000 miles per hour roughly, how long would it take us to go across this galaxy in our spaceship? About 2 billion years, just to go across our own galaxy. And when you have done that, what you have accomplished is you have gone across this little dot in 2 billion years. And this is one of many dots in this picture, which, remember, is a picture that you looked at from a tiny dot in your cardboard box, looking at a tiny patch of sky. So space exploration is, in this sense, utterly hopeless. Question?
Isn't our galaxy one of the smaller ones that we know about?
It's about average. Yeah, not too spectacular.
Do we know how many light years across that photo is?
At least the-
Oh, across?
Yeah, like from our perspective, it's several inches, but obviously it's much.
Yeah. I don't know. The question of yeah, you can do. It's the ultra deep field image, so it's the question of how far back they're looking. So again, this is another amazing thing about this photo, is that this galaxy that we're looking at it the way it was probably, a billion light years in the past. Sorry, a billion years ago or something. So when they look at us, they don't see us. They see what was going on over here millions or billions of years ago. So, but yeah, I don't know what the coverage here is. It'll be like, you can do the math of like a cone going out for whatever that distance is, and then see what part of the sky it covers. All right. This right here is an image of the Milky Way galaxy from somewhere on Earth. I think it's in Nevada somewhere. And has everyone seen like the galaxy in the sky? Has anyone not ever seen it? Okay. I have not really looked at the sky until I came here to UNG and I had to teach a course in astronomy. That's when I went and learned about what is the Big Dipper and all that kind of stuff. And so I had never really, I lived in big cities my whole life. And so I never really looked up at the sky. So there might be some of you that have never actually seen this. In Mesa Verde, where's that? Is that a place somewhere on Colorado? Okay. Excellent. So what are we looking at here? So this, so if you look at the sky, it depends on where you are and what time of year and all that kind of stuff of how it appears in the sky. But basically, this sort of line or this sort of foggy patch that goes across the sky is our Milky Way galaxy. And it looks the way it does because we're within the galaxy and we're looking at the galaxy from within it. This is what we see. So to give you a little perspective here, you can think of our Milky Way galaxy. It looks like kind of like a UFO. So it has, something like this, or maybe I should make it more symmetric. Something like that. So somewhere in here is a supermassive black hole. There's a bunch of collection of stars here towards the center. We live somewhere out here in the burbs of the Milky Way galaxy, about 8 kiloparsecs away from the center. Nowhere special, we're just here. And how does that relate to this picture that we're seeing here? Well, what we are seeing is we're in this galaxy. It looks like a sort of a pancake, kind of. It's a flat kind of thing. Back in my day, we used to have these things called CDs, which you guys don't know about probably. But the aspect ratio of our galaxy is like a CD. So if you scale up a CD, it will look like our galaxy. If you scale down the galaxy, so it's about, I think the aspect ratio is like 100 to 1, where I think it's about 100 times across. Sorry, the size across is about 100 times the width. So this thing here is about 100,000 light years, this distance here. And then this width of the galaxy, this is about 1,000 light years. So how do we explain this image on the left? Well, what is happening is that we're here, and if we were to look away from the plane of the galaxy, away from the batter of the pancake, if you will, then we're looking out into space and we don't see a lot of stuff. So that corresponds to looking out here or looking out there. So you're kind of looking somewhere here where there aren't a lot of stars. And what is this thing that you're looking at here? That's when you look within the plane of the batter. So if you look this way and this way, inside the plane of the Milky Way, then you see this kind of ring of stars, because there's a lot of density. Well, it's all relative. As we know, the nearest star to us is really far away. But from this scale, the galaxy is a more dense region of stars than out in outer space. So what we are seeing is basically this ring, and that ring is what's going all the way across. It's basically a circle all the way around us. Yeah.
Is the universe expanding at a fast enough rate that we will notice like a change in the way this looks in our lifetime?
Not in our lifetime. Yeah, in our lifetime, it's going to be basically, we won't notice anything. So the sun will go out in about another 5 billion years. So that's when people will notice a big change. But yeah, you can extrapolate. It's a good question. What happens way in the future? I don't know, bazillions of years from now, because the universe is expanding, everything's moving away from us. A lot of these galaxies and stars out here will fade into the distance, and the universe around us will get darker, will get more and more lonely, yeah. So, but we'll all be dead by then, if that comforts you. Okay, any questions on that? And I just an interesting fact is there is a star constellation called Sagittarius. Let me see if I can find it somewhere in this picture. So by the way, these dark patches that you see here, these are from interstellar clouds. They're kind of extinguishing the light coming from stars behind it. And you can see here that this galaxy gets a little bit wider over here, and then it's kind of a narrower thing here. So whenever you're looking at this thing where it's wider, you're looking in this direction towards the center of the galaxy. And there is a constellation of stars called Sagittarius. Holy crap, I think I actually found it. I think it's right here. Yeah, let me actually draw it. This is amazing. I actually found it. This constellation of stars, I think there's like a little, maybe I messed it up, sorry. Yeah, let me do it this way. There is a constellation of stars like this. And I think there's like another star somewhere here or something. So it looks something like a teapot. That's called the Sagittarius constellation. And you can actually see it in the sky. And the idea is that this teapot is like, the steam is coming out of it. And that's how you can kind of locate it. So if you, I think around now, if you were to go out in the late at night, you would be, if you look south, then you should be able to spot this constellation. It looks very big in the sky. So these things are very spread out, but you should be able to spot it. And you get all these little apps to help you find things. So I would recommend you do that. Any questions on that? Okay. It gets much worse.
It's worse.
I guess I mentioned this already. Our galaxy is one of 100 billion. That should probably be trillions of galaxies. I should update that number. You might ask, what is the time it takes for us to go to the next nearest galaxy? So we're this little, maybe we're this dot here, and I want to know how long it takes me to go from that dot to this dot. And again, all of this is within a tiny dot in your cardboard box. So how long does it take there? The nearest galaxy to us, major galaxy to us, is Andromeda. It's about 2.5 million light years away. So again, if there's aliens on Andromeda looking at us, they would not see us. They would see whatever was here 2.5 million years ago, and vice versa. You can do the same calculation. How long would it take us to go to Andromeda with our current spaceship? It would take us about 56 billion years. The age of our universe is about 13.8 billion years, so many times the age of our universe. Just to go from one dot to this other dot, among all these dots, and this entire image is one of many, many dots in your cardboard box. Cool. So if you're freaking out about a test this semester, just take comfort that it doesn't matter.
Yeah.
All right. This is the, since we're getting all philosophical here, this is the pale blue dot image. Have you guys heard of this before?
I've heard Carl Sagan speak on it 1,000 times.
Say it again?
I've heard Carl Sagan speak on it 1,000 times.
Yes. So this is there used to be an astrophysicist named Carl Sagan. What you're looking at here in this tiny spot is planet Earth. This sort of beam of light here is just sort of an optical effect. And the way this picture was taken, it's actually the world's most amazing selfie. Because we sent out, I think this was on Voyager 1 or 2, I think Voyager 2 maybe. This satellite went out, and it's still going off right now. But at some point in the 80s, it went a little past Pluto, and Pluto is about 3 billion miles away from us. And right when the spacecraft was somewhere here, Carl Sagan, because he's Carl Sagan, he was able to make a request to NASA, and he said, can we turn the camera on this satellite around and take an image of us from this perspective? And people at first were like, well, that's really stupid. You would just see a tiny little dot. What is the point of it? And his point was, that is the point. All kinds of puns in there. Because we want to see ourselves as this tiny point in this vast universe. And so these rays of light here are just some lights bouncing off of the mirrors on the satellite or something like that. It just happened as a coincidence that we happen to be suspended in this light beam. And Carl Sagan was very poetic, so he would say things like, we're a mote of dust suspended in a light beam, blah, blah, blah. We're all here on this tiny little dot. Anyway.
Why are we not able to see anything around?
So again?
Why is there nothing around?
There is, but everything is very far away. So in this, yeah, space is very, very empty. So it takes you a long time before you hit something. Yeah. Here's a quick calculation, another one. We've been through units quite a bit. The age of the universe is about 10 to the 17 seconds. I'll just kind of leave this for you to read on your own. You might ask, what is the age of the universe in years? So you can convert from seconds to minutes, minutes to hours, hours to days, days to years. And so if you do that, you get about 13.8 billion years. Any questions on that? Okay, so I'm going to switch gears here, and I'm going to, once and for all, talk a little bit about significant figures, because eventually when you do your WebAssign things, I'll always get emails about how many digits should I leave in the answer. I will not worry too much about significant figures, but I will quickly tell you what they are. If there are questions about significant figures, then you should know what they are, but I'm not going to take points off if you leave too many digits or too few or something in some unrelated problem. But you don't want to like put all 10 numbers in your calculator. So just to give you a sense of what that is, let me quickly start this part. So what is the idea of significant figures? It is a quick and dirty way to communicate how confident you are in every digit that you write down when you write down some number for a measurement. Okay. So every experimental measurement has associated uncertainty due to various effects and limitations, the limited accuracy of the experimental apparatus, the skill of the experimenter, the number of times the measurement is carried out, like statistics, how confident you are. So the value of a measurement is really meaningless if we do not know the uncertainty associated with the measurement. So if I tell you there's a car going at 55 miles per hour, you're like, okay, that's great. But then the next day, if you come and tell me, well, the error on it was plus or minus 40 miles per hour, then you really don't know what the speed of the car was. It could have been 10 miles per hour or 90 miles per hour. So the meaning, unless you, but if you tell me that the uncertainty on it is only 2 miles per hour, then that the 55 miles per hour has a whole new meaning in the context of a smaller uncertainty. So here is an example of the uncertainty from the limitation of an experimental apparatus. So here's a ruler, and you're trying to measure the length of this pencil. Well, the ruler has some inherent limitation in accuracy. It has these tick marks, so it can't measure anything to a resolution smaller than the size between two tick marks, right? Because there aren't enough tick marks in between them. So therefore, here you say that, okay, you're measuring this to about 7.1, but then you put in plus or minus 0.1 because you don't know if it's 7.2 or 7.3. So there's a little uncertainty there. So that's one way in which you would estimate the uncertainty, just by looking at these tick marks. So the true value can lie somewhere between 6.9 and 7.2. So a way to convey information about the uncertainty in experimental measurements, the number of reliably known digits in a number is called significant figures. And again, to give you some context, there's a whole separate subject on quantifying uncertainties in various things. It's a whole field in statistics, etc. And so if you are doing something very, very serious, like a high-end research or engineering or some lab work, you want to do it much more carefully. But if we're doing something where we're not all that concerned with it, we're just doing quick things, significant figures is a good way to do it. Okay, I think I have only 2 minutes left. So let me maybe stop here and we will talk about significant figures and probably start chapter 2 in the next class. Have a good weekend. I will see you guys on Monday.